color coding has become necessary primarily because the uh, the use of hydrogen for various applications can be promoted only and only if it is coming out of a sustainable source. Otherwise, it is making no sense to have fossil fuel or electricity generated out of fossil fuel and use hydrogen as a transportation fuel or any other source of fuel. So the first challenge was to make sure that the hydrogen coming out in the market is coming from a green source, which is renewable energy source. The other variants of the color, as the technology is developing, these colors are getting developed. I mean, the last of the lot, the white hydrogen, which is coming out of the process called as fracking. And in the US, most of the natural gas is available out of fracking, which is coming from the rocks underneath the ground. And it's a kind of geothermal process which converts fossil fuels into hydrogen or mix of other fuels. This is not very popular, but all the other sources of hydrogen with other colors, they are quite popular. Now, let's come to the Indian scenario of the green hydrogen definition under the National Green Hydrogen Mission. Now, this is very latest, August 2023, this has been declared. Now, this understands that green hydrogen shall mean hydrogen produced using renewable energy, which is like the definition world over, which is including but not limited to production through electrolysis or conversion of biomass. Now, this is a very important part. This conversion of biomass is otherwise not recognized as a green source of hydrogen as of now in the rest of the world very clearly. Now, in India now we are recognizing it, and the renewable energy also now includes such energy generated from renewable sources, which is stored, etc., etc. Now, which means that this definition helps us to work on waste to produce green hydrogen. Now, I will show subsequently why this is a very significant and very important step for the country as a whole. Because as a country, we are having a dream to go for a decentralized hydrogen generation. We don't want to have hydrogen generation at one place and continue to transport it all over the country. So when we are doing this decentralized hydrogen generation, we can now look at all sources including biogas, biomass, municipal waste, industrial waste to come to terms of it and convert it into hydrogen and further chemicals which can come out of hydrogen. And they are getting color coded now. So for example, we have now green ammonia, which is a source for fertilizer making, coming out of green hydrogen, which is coming out of the process defined here. And for the renewable energy, the hydrogen from waste, including wastewater through microwave route, etc., it has to come out of a process with 2 kgs of carbon dioxide equivalent per kg of hydrogen GHG emission. Now, this is a very good step government has introduced, whereby we have started to define what exactly we want and how we want it to happen. Now, we have a typical SOEC electrolyzer, that's a technology. Now, electricity which is coming out of non-biogenic GHG emissions, which are lesser than 50 grams per electrical unit, needs to be used. But it is not restricting us to use these. The rest of the world does not allow us to use the waste as a green source of hydrogen, and therefore the process has to be necessarily electrolysis only. You know what I mean? The process is completely driven by a technology world over, where in India we are now allowing other technologies to participate, and gasification, which is considered under black hydrogen if we are trying it from the coal. Instead, if we can generate it out of biomass, then it will become green hydrogen. Now, this, in my opinion, is a very, very significant step because we are also generating electricity from concentrated solar power, you know, or the heat which is coming out of concentrated solar heat generator for producing steam and electricity, and then by using electrolysis or electrophoto-splitting, whichever process we consider viable. Internationally, as I said earlier, the color of hydrogen coming out of biomass is yet not defined. It should include, but it is not including today. So, therefore, a reasonably proven technology of gasification, which is commercially available, is not possible to generate green hydrogen on an international scale. But within India, as I said, in this definition of MNRE, we have given a clear roadmap that we accept this as a green hydrogen source. Now, without this introduction, the cost of hydrogen cannot be brought down in the capex and in the opex model. I will show in the subsequent slides. So, the moment we go to this route of biomass MSW, gasification route, then it can fulfill India's dream of decentralized hydrogen generation at the point of use. So, when I'm talking about point of use, what are those touch points where hydrogen can be used as a fuel? So, one of the prominent and very, very direct use is to use light and weight, heavy and light vehicle fuel. Hydrogen itself can be used as a fuel. So now we have got hydrogen as a fuel driven cars available commercially. Also, hydrogen can be converted to fuels like dimethyl ether, ethanol or methanol, which can be blended in the current gasoline or petrol, and we can generate available rich gasoline or rich petrol, which can be used, or rich diesel, which can be used as a fuel. So where we can substitute partially or fully the dependency on fossil fuel. Now, fuel cell can become a future substitute to DG sets, particularly for cell towers, which is like your mobile cell towers. At remote construction sites, it is being immediately tried. Reliance Jio has done a good work on this front, and they are moving ahead with a massive program on fuel cell to electricity for their geo, cell sites. One day it can come to the kitchen and substitute LPG or PNG. Now the trials have been very successful, whereby the hydrogen generated cannot be transported for long distance, but it will be injected in the current CNG lines, where domestically generated hydrogen at a decentralized location will actually substitute imported LNG or CNG. Now, on the face of it, they may sound very little interventions, but they are very, very significant. Which means somebody has got about 20 to 50 crores of investment ambition, can generate hydrogen and can inject this hydrogen into the national grid of gas without having to convert it further, transport it further, and store it. Because hydrogen storage and transportation world over is becoming still a challenge. It's not resolved. Because it's a very light gas. Being a light gas, it has got a very high volume. So it has to be stored under a significantly high pressure of 300 atmospheres or 300 bars. So the entire piping, storage vessels, everything related to this storage at 300 bars is a challenge. To overcome this challenge, the Indian think tank has provided a very, very reasonable solution, in my opinion, where this gas can be injected directly in the available pipelines of GAIL, and equivalent remuneration can be recovered at the point of generation. So the point of generation and point of use, the market, are getting closer, and therefore decentralization is possible. The next step is methanol or ammonia. These would be two chemicals to watch, because the hydrogen generated can be converted to ammonia, and ammonia can be transported as a fuel. And green ammonia fuel transportation as a potential substitute to uh, commercially available crudes is world over accepted. And India is working out to be a hub for this green hydrogen to ammonia, I would say, transition. And it's a global transition, and India would definitely have an advantage of its large biomass reserves to generate this hydrogen. Methanol, on the other hand, can be a starting chemical for every polymer oblique plastic we think of. Whatever we can think, polypropylene, polyethylene, polystyrene, polyester, whatever polymer we think of, today it is coming from natural gas, tomorrow it can come from methanol. Now, again, this is a game changer, because this methanol can come from our biomass, which is a waste today. Wherever there is a commercial exploitation of biomass, there is a waste generated. You pluck out cotton from the cotton bush, and the cotton bush is available as a biomass. You take out groundnuts from the groundnut shell, and the groundnut shell becomes a biomass available for all these activities. You take sugar out of the sugar cane, and the bagasse becomes biomass. You have parali as a challenge today. Parali can be a resource tomorrow. So paddy, has mustard, everything what you can think of as a potential bio waste today. Tomorrow it will become a source for hydrogen, ammonia, or the chemicals which we are using. It will gain enormous commercial value, and the idea which the country is working with is that the last mile profitability can be improved with these kind of interventions. Of course, there are challenges, and there is nothing without a challenge. Biomass challenge is the availability on a continuous basis as a bulk producer of chemical. Biomass is relatively cohesive composition. You have a very decently defined composition of biomass. So it is defined to have impurities, and those impurities can be finally treated, and it can go easily to the final chemical product. When one wants to use it as a fuel, there are no challenges, because whatever you put in will burn or will come out as ash. But if you want to convert it into chemicals, then the decimal grade purity becomes a challenge. Now, cost of biomass is increasing very significantly, because the use obviously is becoming rampant and significant. On the other hand, municipal solid waste is available in abundance. We don't know what to do with it. We have mountains of municipal solid waste all over the places, but it does not have a cohesive composition. So you take a mixed waste coming fresh from the homes and getting delivered to a site, you have a different, I would say, composition than a legacy waste which is lying idle in a place or a premise for years. And the kind of difference is, from a fresh municipal waste, one can get about 50% fuel, RDF, rich derived fuel. Whereas from a legacy waste, that number is 50%. It is only 25% RDF. So which means that per 100 ton treated municipal waste, which is fresh municipal waste, we can get about 50 tons of fuel. Whereas per 100 tons of legacy waste, we can expect only 25 tons of fuel availability. Municipal corporations and government can give a very committed supply of MSW. Now, this is a very, very important aspect. Biomass availability is seasonal and absolutely non-controlled. Non-controlled means it is completely in the hands of unorganized sector, and the long-term contracts are not possible. You are going to individual farmers, asking them to sign a contract with you, and those contracts can be anytime turned back, and somebody gets a penny more or a pound more, and somebody moves out of the contract for a penny or a pound gain. Whereas for the government and municipal corporations, these are long-term contracts. When I'm saying long-term, somebody can base an entire life cycle of a business, 15 to 20 years. And the municipal corporations can sign a contract for 20 years of supply. We ourselves have done a project in Manipur, Imphal, where we have got a 15-year contract for the MSW supply. Now, this is not possible with biomass very easily. The last and foremost challenge for everyone is that the scale. All technologies today commercially available are at a large scale. Now, you do not have a small capacity methanol or a urea manufacturing plant commercially viable. Now, after having said the challenges, let's look at what is possible. Otherwise, it would sound as mission impossible. It is not. The first step to get out of municipal solid waste is to get to syngas, that is a synthesis gas, which then is versatile, can be converted to electricity, chemicals, hydrogen, whatnot. So I'm going to run through a small case study today where we have physically installed a plant which is generating electricity from this municipal waste, which is further going to be being used as a raw material for the raw energy source for an electrolysis process to generate hydrogen. So this is the route by and large. 100 tons of municipal solid waste, the syngas route will, through gasification, will give synthesis gas, which will generate power, which will generate hydrogen. So about 100 tons per day of waste can generate around 0.8 to 1 tons per day of hydrogen by electrolysis route. Now, why I'm showing this slide? Because this is something which is working. This is the plant. What you can see at the bottom here was the concept model that was prepared. And what you can see here is the finally erected complete plant. This is in Noida, NTPC. This is inside the plant. So what we've done, we've got municipal solid waste coming here in the form of briquettes. Those briquettes are transferred through this conveyor to the gasifier. Now this is a gasifier. This gasifier generates a gas which is synthesis gas or syngas, popularly known. The other popular name for it is producer gas. This then goes into heat exchangers and cleaning mechanisms. Post all this cleaning of the gas, this clean gas is stored in a balloon, and from the balloon it goes into the engine. Now this engine generates electricity. So this entire plant takes 15 tons per day of briquettes and generates 600 kilowatt of electrical energy. Now, whatever I'm showing you here, I would definitely like to show you a live video of that. Now, this was done by a company, Thermotech Systems. We had done the entire engineering of this project from concept till commissioning. There is a fuel preparation system, there is a gasifier, syngas, then electricity generator. These are the briquettes what we aim to have. And these are actually the pile of briquettes what we have. So besides municipal waste, these kind of fuels can be used. So this was project commissioned last year. As I said, what you see here is at the blueprint stage what we had conceived. These were all 3D drawings. Here what you can see is the route. Now this is actually the waste which is coming to our site. This is physically what we receive. I am very proud to say that all of it is converted finally into a very clean solution. Then it goes to shredding machines. From the shredded biomass, which you can see here, this is RDF. It has got plastic, it has got paper, it has got everything what you can see in a waste, which goes to a briquetting machine. So there are briquetting machines which convert this pile into a briquette. Now what you can see is a briquette made out of municipal waste, which is then conveyed to the top of the gasifier through the conveyor, which is a feeding system. It's a tall 18-meter high structure. Now this is the gasifier, which is the reactor. In this reactor, the whole waste briquettes are converted into finally a combustible gas, which is taken to this heat exchanger, and the other cleaning, this is the cleaning device for gas. Any tar, fine particles are removed. This is the terminal cleaning of the gas. This is a final dehumidifier processor. Then the gas is completely cleaned of any impurity. Then it is put into the balloon. As I was telling you, this is the balloon where the gas is stored. This stored gas is then through the blowers put into an engine. Now what you have in front of you is the engine. This is the engine. This is given by Siemens, and Lori Sumer is given the alternative. So you can see it's a very established supply chain. It's not run-of-mill kind of supply chain. It's properly engineered, completely well-designed system. This is the engine, which this is a 700 kilowatt engine derated to 600 kilowatt power generation. Then we have a final flue gas scrubbing. Then it goes to the chimney, and from the chimney it goes out to atmosphere. What goes to atmosphere is completely clear carbon dioxide. We have a continuous monitoring system of NOx, SOx, chlorides, and hydrocarbons. Everything is as clean as a DG set exhaust, what you can see in your back cabin. It is as simple as that. These are the power synchronizing panels. This is the power generation module. So this is completely PLC based power generation. On a SCADA, it is integrated. Now, Thermotech as a company has been providing this, and we have been working on the entire chain of engineering. So, as I was trying to show, coming back to the presentation again. So, what you saw here was the complete chain from the briquettes to the power generation. I think the video would have made it very clear for somebody. Now, if there are any questions, I request you to raise your hands. We would be moving to the next point, which is what else we can do from the same technology. But if there are any questions on the electricity generation from municipal solid waste, the commission plan, you can raise your hands, and Bhavna can probably take those questions maybe at the end or in the beginning, depending on the schedule of the program. Now, processing of MSW, that is municipal solid waste, to hydrogen and chemicals. So the 100 tons of municipal waste, if you remember, was giving me 1 ton of hydrogen by electrolysis route. If I go by a chemical gasification route, I can expect the generation to be 2 tons, double of what is possible out of electrolysis. Now that is why biomass conversion to hydrogen or MSW conversion to hydrogen directly makes a huge sense. You get double the amount of hydrogen for half the amount of power, because your electrolysis consumes about 50 kilowatt of power per ton of per kg of hydrogen, and the gas separation process consumes less than 20 kilowatts of power. In fact, we're working on a model where it can be per kg, it can be brought down to less than 10, which means the overall energy impact in terms of the consumption per generation is very, very optimal now. Along with that, you get 36 tons of CO2. Now, people think CO2 is something bad, no, not worth to have. That's not true, because the fundamental fertilizer what we use in this country or world over is urea. And urea is nothing but carbon dioxide connected with hydrogen and nitrogen, which combine to make ammonia. So ammonia and carbon dioxide make urea. So for a conventional urea process also, this entire CO2 is a raw material required for making urea. The other options, we can go for methanol, 8 tons per day of methanol and about 0.5 tons of hydrogen with 25 tons of carbon dioxide. And instead of methanol, this hydrogen and this methanol combined will give ethanol. So instead of 8, we will have about 6 tons of ethanol and 25 tons of. Now, ethanol is even today a popular fuel. We have ethanol mixing in petrol going up to 20% now. If this comes from this waste, municipal waste, this is a game changer. And this methanol, methanol, is the game changer for the plastic industry. And this can be a fundamental raw material for the plastic making. Now, just to come back and summarize, the synthesis gas, what we were talking about, this is the green product produced synthesis gas. Via hydrogen, it can give ammonia, chemical, or it can run fuel cell. The same synthesis gas can be used for power generation. Reliance has a pet coke to power mission, and they have a plant which is running completely. The refinery is completely running on synthesis gas to power generation route under the J3. It can convert to methanol and it can give ethylene to polyethylene, acetic acid, formaldehyde, dimethyl ether, methyl acetate, polyolefins, petrol. Then we have a process of Fischer-Tropsch. If we can take this synthesis gas through this route, we can get naphtha, we can get petrol, we can get diesel, we can get wax. This gas going to synthetic natural gas is possible. For iron reduction, iron ore to iron, this gas is very useful. Now, whatever I am telling you today may sound like some fairy tale, but believe me, the world history would have been different if the Germans would have been the winner of World War II, because they had nearly conquered all of this. This was the route which the Germans were working on, with coal as a basic fuel and everything else. They had automobile working on this syngas already. Even in India, we had domestic gas pipelines where the synthesis gas was being fed. Somebody may remember, the olden days of Petromax bulbs that was used for street lighting. Those Petromax bulbs in some part of the country were run with this kind of gas, synthesis gas. In Mumbai, that is the city Mumbai, in some part of Mumbai, Shivdi, Bhaika, Masgaon, in that area, we still have these old syngas pipelines laid to the individual homes. So this is not something which is unreal. This is something real. This is a history which we were not taught in our chemical engineering college, because the Gulf available petrol and diesel, instead of coming from this route, was coming in more easily from the Gulf region. But now we have a chance to work on these and get them to move. So mind you, this is going to be soon coming. So in conclusion, I would just like to say that it's no longer just an academic thought. It's a very well engineered solution. There are projects that are already under execution. Technology maturity level, TML, if you see, or technology readiness level, TRL, for municipal solid waste or biomass to hydrogen is close to 100%. In fact, IISc Bangalore has already got the patents from biomass to hydrogen for a certain starting biomass, and it can be commercially available for any venture. So people were really serious about business in this line. This is no longer a fairy tale. Now, the approach we had to this problem was two-pronged. We wanted to address two issues like sustainability through pollution of municipal solid waste. The land which is blocked by municipal solid waste should be free. The pollution subground, the pollution above ground is known, but the pollution subground can be eliminated. We have got millions of tons of legacy waste lying all over the country and the rest of the world. So we've been getting inquiries from the rest of the world. We are working on now projects beyond India. We're working on a project in Canada where they have a lot of agricultural waste, which we will be converting into chemicals, biofertilizers. We are going to work on biofertilizers and biopesticides. Again, it is not a fairy tale. This is something we are going to dispatch in the next couple of months. So my point here is that we are going beyond theory now. And all the audience here, I would like you all to believe that the transition and the revolution has begun, and we can expect to see results. And anyone interested in these can reach out to me or my company or to Bhavna or AEEWI. For any further, we will be glad to provide all the possible inputs and see to it that this doesn't remain a paper talk, it becomes a mission by itself. So thanks a lot, and over to you, Bhavna. I mean, sorry for the small technical glitch, but I think I've covered it in my given time. So if there are any questions, open for them now. Thank you.
Thank you, Rajesh. That was wonderful. And really, I mean, hydrogen is a future, as is being said. Now, before we move on to other questions, I have one question. So,
Okay.
I mean, how does economics will work out, or is it already in place? Like whether it is a cheap.
Okay, let me. Good question. I mean, actually, let's put in the perspective. 1 kg of hydrogen in terms of energy is equivalent to 4 kgs of natural gas, PNG, piped natural gas, what we get. So we have around 65 rupees is the price the customer pays for natural gas. So 4 times of 65 is roughly 260 rupees, which is like $3.50. Now, from the conventional electrolysis route, the cost comes to about $8 per kg of hydrogen, considering the stored electricity in the batteries and use. I'm talking about green hydrogen only. I'm not talking about any other hydrogen. So now, online hydrogen production, the step jump is already done, and it is now available close to $4.50 a kg, which is 360 rupees a kg. So 260 versus 360 is the 100 rupee, I would say, gap currently being seen. But if we go through the gasification route, then we can match definitely the price of 260 rupees. And in fact, IIS has already come out with a clear understanding that it will match the price of natural gas on the energy parity. But now the but is, why are we generating hydrogen? We don't intend to generate hydrogen for the purpose of energy. Now, when we go to chemicals, say for example, when we want to go to the fertilizer or ammonia route, from natural gas, we have one more step of cracking, that is reformer, steam methane reforming to get hydrogen. So that step is eliminated when we are getting directly hydrogen. So for the chemical manufacturing process, the purchase parity is already inside. It can be seen now.
Okay.
That I would.
Yes. That was very clear. And now Mr. Deshpande, he has. Yeah, Gopal, you have raised your hand. Mr. Gopal, you can speak because I have already enabled you. Okay. Till then, we will move to other questions.
Yeah.
Okay. Can you hear? Yeah, Gopal. Okay. Let's move to other questions. Yeah, Mr. Ravi Kiran, his question is, you mentioned briquettes are having plastic content in it.
Yes.
So that's what is his question.
Okay, the briquettes are made out of plastic and paper and cotton waste and polyester and everything together. Now we have a misnomer that plastic combusted gives pollution. It's not correct. It is only the PVC which has got chlorides and certain other plastics which have got some other chemical content can cause anything which is harmful. But the most popular, I would say, most popular plastics as a generic term, polymers, I want to say, have, say, for example, polypropylene, polyethylene, they are all pure hydrocarbon chains. And whatever is available commercially as a waste, because most of the plastic which is having anything else than hydrocarbons is recycled. And if I want to get any, PET bottle, whatever water we drink is through a PET bottle, I will not get any, not even 1 kg of PET bottle in hundreds of tons of waste, because that is already recycled. And we have plastic recycling plants generating PET again. So what we get in the waste, the plastic we get in the waste is generally HDPE, PP and polyethylene, which absolutely are flawless when we use it for combustion. And mind you, we are not letting anything which is coming out of the gasifier to atmosphere. We are converting everything, again combusting it again and converting everything into carbon dioxide or H2O, that is water. So there is no pollution because of plastic. In fact, now we are working on pellets made out of plastic RDF that can be directly combusted in the boilers. So we've already taken trials successfully. So anybody wants to replace their briquettes or coal with these pellets, it is available.
I hope that answers your question, Ravi Kiran. I mean, rather doubt that yes, plastic is allowed here. And now we have question from Mr. Kavishwar Prawar. So he has given 3 questions. I'll read out all of them. What is the pressure output of syngas? And second question is, what is the cost for setting up a 600 kilowatt plant at NTPC? And do we have syngas generators readily available for such commercial use?
To answer the questions, yes, the syngas which is available out of gasifier, there are multiple designs of gasifier. The most popular is updraft gasifier, where the gas is practically having zero pressure. But there are pressurized gasification plants available, fluidized bed and pressurized gasification plants, where the syngas pressure can be higher. Roughly, it takes about 15 crores to set up a 600 kilowatt to 1 megawatt power plant, starting from RDF briquettes. Now, the cost can be brought down significantly if we have readily available engines indigenously. And we have a couple of engines developed and we are trying on that. So the cost can be significantly lower. Commercial syngas engines are available, and there are more than one European supplier who are guaranteeing the output. Incidentally, we have a very good experience with the Chinese supplier for the syngas engine, which we are using in Manipur. So we have currently experience with Siemens and Shandong, which is a company in China, and both the engines are really good. So I think I've answered the questions.
Yes, Mr. Kavishwar, I hope that answers your question. And you can again get in touch with Rajesh. His email ID and mobile number are there. And for further questions, if you have, since you are having a live case with you to work on, so that will be very useful to both of you. And again, Mr. Ravi Kiran is asking about the quality check. I think he refers to that plastic.
Yeah, plastic quality check is very much possible, and all norms of quality control and the pollution control can be met without any challenge. So, in fact, I can read out the next question also because I can see now questions.
Yeah.
We can use hydrogen instead of LPG heat treatment furnaces, correct? The answer is yes. They are actually more useful and less polluting compared to LPG. The combustion system cannot be same. The burners will have to change. So, as I said, hydrogen is a very low density and high energy contained gas. There would be modifications in the burners that are required, but now hydrogen burners are available, and you can also mix hydrogen in LPG and use. So you don't need to 100% substitute. To answer your question, 100% substitution is possible for heat treatment, for forging. In fact, for forging, heat treatment, annealing, and the metallurgical use, hydrogen is presently also recommended as an oxygen scavenger to minimize scaling losses inside the furnaces. So people are using syngas directly for that. And if somebody is looking for heat treatment for Mr. Jayan Deshpande, I would recommend not to go to hydrogen, but better you can work directly with syngas because that will be very, very economic. Against LPG, you will have at least 50% reduction in cost if it is syngas. So cost benefit is like 50% cost reduction from syngas, and the payback would be surely less than 3 years. meters. Calorific value of municipal solid waste RDF is around 4,500. The pellets which are made out of this MSW RDF are around 4,000 to 4,500 kilocalories. Now there is one more way of working which we have successfully tried, because the calorific value is low primarily because there is significant amount of ash in it, around 30% plus ash. So in the pre-treatment, we have removed that ash, brought it below 15%, and the calorific value of RDF is around 5,500. So it can be up to 6,000. That is the target.
Great. So I don't see any further questions.
One more question looks to be, do we have any other product from this gasification process? Carbon monoxide, carbon dioxide, and hydrogen are the three components of it. And further gasification can be used to take the route of methanol, ethanol, and other chemicals. That syngas becomes a starting chemical for all other chemicals to manufacture. So, if anybody wants to write also, they can note down my email and phone number, and would love to be in touch. And if time is available, I don't mind spending another half an hour answering questions. I have no challenge.
Yeah. Definitely, it was a very energetic session, and love the way people are interacting in this session. And really, something meaningful will definitely come out of this session. And we are, as AEEWI Western India chapter, is always happy to connect you to whatever is your requirement. We can connect you to the proper experts. So you can write to us also if there is any requirement of any sort. Definitely we can take it forward. Yeah. So, and regarding award, already the link is shared with you, and you'll also be receiving a separate mailer for awards function. So definitely to participate in that award program, it will be a great platform for everyone to present your work and share and learn from each other. Thank you, Rajesh, once again for having a very nice session. And thank you, everyone, for sparing your time each time, every session. And we hope to see you in good numbers in future sessions also. Thank you so much.
Thanks a lot, Mama. It was wonderfully organized, and I love the interaction. So, hope to be again on some of the seminars on a different topic.
Definitely. Definitely we will have. Thank you, sir.
Bye-bye.
Bye. Thank you.